So let us start with this part and let's solve the Euler's theorem question, because similar approach should be applied just like the Fermat's theorem. So if you remember, we had discussed this Fermat's Little Theorem while we were talking about the prime numbers, and we found out that there's an easy way out in solving very complex kind of power problem when there's a very high value of n or any high value of p for that matter, prime number. Then in all those cases, we can use the equations 1 and 2 to solve very easily what will be the resultant without even computing anything. So for example, we took this two small examples. One was 6 to the power 10 mod 11. In that, what we observed that the power 6 to the power 10, if you observe, that follows the first law, which is this one, a p minus 1 mod of p. So if you observe here, p is 11 and p minus 1 is 10. So the power and all that forms the first law. So we directly, without even computing anything, we can say it as 1. The same thing you will observe that when we discuss Euler's theorem, we will do the same thing, except that there will be a Phi-Function that will be added to it. Rest of the things are absolutely the same. Alright, it will also have a process to find out inverse, multiplicative inverse and all those stuff. So it's the same thing, except that the equation might, like Euler's theorem is basically a generalized equation to that of Fermat's theorem, if you say in that way. Because here it is specific to prime numbers, whereas for Euler's theorem it is applicable to any composite numbers as well. Prime number to definitely, but along with that composite numbers it can also be applied. So it's a more a generic approach to it. So I'm not wasting much time here. This part is very important. Remember, we had solved specific questions on how to find out the inverse of this kind of question, 8 inverse of mod 17. Because as I said, in the multiplicative inverse that we have computed so far, it was more like find the inverse of 10, find the inverse of 15, find the inverse of maybe 1, 2, 3, 4, like that. But it is the inverse of an inverse. So basically it's an 8 inverse we are giving. We have to find the whole number that is there. For that, we have solved some process. And if you remember correctly, that the basic rule that I told you, that make sure that the power, first of all, the first line itself, the first line that you are looking at here, over here, this part, this is nothing but the application of the rule itself, which says a to the power minus mod of p should be represented as a to the power p minus 2. The first thing that needs to be considered, that this to the power minus 1 needs to be reduced to p minus 2. That's the first thing. That's why this to the power minus 1 has been converted to something as to the power 15. That's the first step. We need to remove that inverse. You will find that Euler's theorem also will do the same thing, except that using a different formula where there will be a Phi-Function. That's it, nothing else. Now the next part comes in, where if the power 8 to the power 15 in this case, although 15 is relatively small number, but the generic rule is whenever you have the power which is significantly high, we need to decompose it in such a manner such that they will constitute the same power value, but it will be of lesser quantity. And the reason behind this is, there's no basic reason. The reason is that more the number of power, you can observe here the particular example 209, this won't be computable in your computers or in fact in your calculators for that matter. For that, we need to decompose this 209 in their power, respective power, keeping in mind another observation that I told you, that this is nothing a rule that makes sure that at least one of the factor is relatively small. Like in this case, it was 22 to the power 4 we took as one of the example, and the rest of the things were taken care of with certain techniques of decomposition. Alright, so that's what we did. The similar process we are going to do today. So those who missed the earlier class, please go through the recording when I uploaded. Most probably today I'll be uploading it, and also find the course material, because why I'm telling you this, in most of the books when you go through, they will only give you these final answers. The internal steps which had gone through, why we are getting that answer as 15 mod 17, for example, the first one, why the answer is 15, it won't be there in any of the books. It won't be explained in any of the textbooks. Okay, so the steps which will be given in the course page as well as in the video when I did in last day's class, please follow that steps. Without that, you are not going to find this final solution. All right, so that's the basic trick. All right. So keeping this assumption, let's go ahead with the Euler's Phi-Function. This is what I was talking about, that it's a generic generalization of the Fermat Little Theorem. So Euler's Phi-Function is represented by some function called as phi n. Alright, it is a representation which is sometimes called as Euler-Stoichern formula, and it plays very important role in cryptography. Why? Because you will soon find there will be a formula, I'll mention it over here. It will be looking something like, let me show you, maybe. This one, this second formula, don't write it, I'll come back to this. This second formula that you're looking at, a to the power k into phi n and all, this particular formula is the basis of the RSA cryptography algorithm as part of the asymmetric keys encryption. So basically this particular formula will be utilized there. But as I've been keep on telling you, that all this we are doing is the mathematical fundamentals which will be used at some time later. So this particular formula as an Euler theorem, Euler Phi theorem, this will be utilized later. Right? So that's one of the significance of it. So let me go back to the basic first part of it. So Euler's Phi function is what we are discussing. So if you observe that what exactly we do it with this particular function, very, very important is the 4 rules that I've given, 4 properties. Please make a note of those properties. The first thing is that it finds the number of integers that are smaller, both smaller than n and are co-prime to n, where n is the prime number. Alright? Or any number for that matter. Okay. So if you observe for that matter, the example 5, this one. Alright, this one I'm talking about, 5. Okay, 5 functions. So in this case, you can see there are 4, as it is a 5. So naturally we'll have 5 elements. 0 will eliminate. So 1, 2, 3, 4 will be the values. Now in this case, what is happening, you can observe that all this 1, 2, 3, 4, they are co-prime to the number 5 itself. So we will say that there are 4 such prime elements, or the function is giving us a value of 4. It means there are 4 such prime numbers which are less than the number itself. On the other hand, if you observe the second one, 5, 6. Okay, please make a note of this. 6, if you observe, the elements are 5. 1, 2, 3, 4, 5. In that, 2, 3 and 4, they are having GCD which is not equal to 1. So they are not co-prime. So basically, although we have 5 such elements, for 5, 6, the Phi function is giving us a value of 2. Alright, so those are the 2 elements which is forming the rule. So the logic is, for any given number, you can try to find out the number of integers which are smaller than that particular value and co-prime to it. Then we are going to apply this rule. Now, if you observe carefully, to make it generalized, first of all, first rule you apply, phi of 1 will always be equal to 0. So anywhere you get a 1 as a number, you can apply, if you are applying the Euler's theorem, phi of 1 will always be 0. But the important part is the second one. If p is a prime number, you can see phi p. P is a prime number, then phi p can be written as 1 minus p. So suppose you are given like you try to find out what will be the number of prime numbers for the letter 11, for the number 11, because 11 being a prime number. So what we are going to do, we are going to just substitute in an Euler Phi theorem, or the rule, phi of 11 will be equal to 11 minus 1, 10. So there will be 10 such elements which is less than 11 and co-prime to 11. Understood? So we don't need to find any other solution. We can directly substitute in the second rule and we can get the answer of number of primes which are present with respect to that number. Any given big numbers also you can do the same way if it is a prime. Suppose 211. Now if you go on counting the number of primes which are present between 211, it's not possible. But suppose you apply over here 211 minus 1, so 210. So there will be 210, all the sets will be co-prime to 211, like that. For example. Third rule that you apply, this is also very crucial, we will apply that in some time. Phi of m comma n, if the number that is given can be represented in such a manner that m and n are relatively prime to each other, then we can represent that using phi m multiplied by phi n. For example, you take an example, phi of 77. Okay, phi of 77. 77 is a factor of 11 and 7. Now 11 and 7 both are co-prime to each other. So what we have to do is something like this. So suppose we are trying to find out 77. So this will be mentioned as phi of 11 multiplied by phi of 7. Now, as per the third rule, as m and n both are co-prime, so we can write this as 10 multiplied by 6, 60. Why it is 10? Because we are applying the first law again. This rule over here. Phi of 10, phi of 77 has been decomposed into phi 11 and phi 7. Now, phi 11 forms the second rule. You can see the second rule. If p is equal to prime, then we can write it as p minus 1. So, 11 minus 1 is 10 and 7 minus 1 is 6. So, total 60 will be, so even if the set is of 77, 1 to 77, there will be 60 such elements which will be co-prime to each other and will be less than 77 itself. Understood? So, that's the third rule is being applied. And the fourth rule is where we mostly apply where the power is like the base is more, like the modulo operator that we are talking about, the p, the prime number. Suppose this is pretty high, not only prime but any number for that matter. If it is very high, then we can represent that using this formula, that if we can represent p to the power e, okay, if we can represent by some means, some way down the line, if we decompose the number in such a manner that we can represent that using phi to the power p, okay, p to the power e, then we can represent that into an equation p to the power e minus p to the power e minus 1. So this 4 rule, please make a note. I'll take an example to explain all the part. Please have you noted down all the 4? All right. All right. So this is about the generic rule that I was talking, the last rule actually. So the final observation will be the multiplication of each and every bracket. You can see p e to the power 1 minus, so that this part is coming from one of the functions like phi of p to the power e1 multiplied by phi of, here it's mentioned actually, this one. Okay, so it's coming from this part. But let's see with an example itself that how it works. So for example, phi 13. We want to find out, all right, what is the value of 13. Now, directly we can substitute 13 as a prime number. So, we can substitute in the second rule itself and we can say that 13 is a prime number. So, 13 minus 1, 12. So, 12 will be the function value of phi 13. Okay. So, that's the Euler function phi 13 value will be 12. Now, within that 12, what are the elements that we can find it out quite easily? You can take the GCD of elements within 1 to 13 and you will get the answer that there will be 12 elements which will have the same quality. All right. Now comes to 10. We had already solved this. In fact, I think 77 we took it. So 10, what you are looking at, 10 is a number which is non-prime. All right. But as I said, Euler's theorem will be applicable to co-prime as well, or rather composite elements as well. So what we are doing is we are decomposing it into phi 5 multiplied by phi of 2. So you can see here. All right. And as this is again applicable to rule number, as these are applicable to rule number 2, we can get as 4 into 1. So 4 will be the answer for phi of 10. Now come to the next one. Okay, next one. Any doubt at this point? That's it. Now let's see whether you are able to solve this one. 240 is given. Phi 240 is given. Okay. Now, the question is to find out what is the functional value of phi 240. Now, in your textbook, it will be mentioned in this way, but I'll tell you the steps that is being over here. Now, if you observe 240, the problem is that if you want to decompose it, like if you try to decompose it in terms of two prime numbers getting multiplied, I don't think it is possible. And even if it is possible, you have to search that what should be the prime number if you want to apply the second rule. So the easier way out is that you just decompose, you just factorize 240. Simple as that. So what it's doing over here is 240 like this. Sorry, this is 30. Oh, sorry. This is not correct. This is not correct. 1 minute. 120, 60, 30, 15, 5 and 1. Now, if you observe why they have written that, so you can see there are 4 times this 2 repeats. So that's why the power is 2 to the power 4. Alright, so that's why it is having written. This is the internal steps that has gone through. There is 1, 3 over here, that's why 3 to the power 1. Why, if you observe that it is actually trying to follow the fourth rule, which says P to the power E. So based on that, they are trying to arrange the equation, the numeric value. So even here, 5 to the power 1. Now they apply the fourth rule. What was the fourth rule? If P to the power E, if P is there, so 2, 3, 5, they're all prime to the power E. If it is there, then we can write it as P to the power E minus P to the power E minus 1. So if you observe, this is nothing but P to the power E minus P to the power E minus 1. So if you observe, this individual part, they are individually P1 e to the power 1, P2 e to the power 2, P3 e to the power 3. And they are applying the fourth rule and they are making 4 such element over it. Is it understandable? Is it understandable? Now, can anyone tell me why the answer is 64 then if you are doing this? If you are getting these values, what is this value computed? It's 8. What is this two values computed? 2 and 4. So basically this, along with this, if you add up, like if you multiply all together, the answer is something like this. But before coming to the answer, the point is, for a given element over like this, 240, anything for that matter, you take 100 for that matter, just try doing it. Let's do that. Find me the 500, okay, the value of it. Let's see. So question is, 500 is how much? Exactly. So the easy process should be, with intuition this you can do actually. 100 can be given by phi of something like this, 25 multiplied by 4, and we can say it is a 2 square multiplied by 5 square. So basically this step itself shows, so it is like P of E1, P1 e to the power 1, P of e to the power 2, like that. So this phi, this value of this can be directly mentioned as 2 square minus 2 1, 5 square minus 5 1. This will be 2 into 20, which is. Can you do it for 516, 516? Because 100 was relatively easier. 516, let's see whether you're doing it. So please follow the process, simple process. Divide like find the factors that involved with 516. So 258, 129, 3 you get 43. With 43 you get 1. Alright, so the factors that you have is 2 square, 3 and 43. So you arrange it, 2 square, 3 to the power 1, 43 to the power 1. 2 square is 2 square minus 2 to the power 1, 3 multiplied by 43. So altogether we can say, now the thing is, what will be the answer for this? 160. Right. Correct. So that's the process. So even you are given any set of function, like any value, and you have to find the phi function of it. What is the value using Euler's theorem? Just apply the same rule and you will get it. If it is a prime number, it's easier to find it using the second rule. But if it is not and you are not in a position to find it out, then come factorization and do it. Let's do it. 2 into 42, yeah. Maybe, yeah. So in that way, you actually come across a situation. I didn't write the last step, like 43 to the power 1 minus 0. That will be there, right? So in that way, you can solve any given question, any given big numbers, even if it is given to you, you can solve it in the same manner and do it. As I said in the previous, just before we started off, this individual steps will not be mentioned anywhere in your book. So please, whenever you are solving it, try to use this portion or how we are solving it over here and apply that in the questions. Alright. Okay. So now, we are in a position. So this already we have done. Now let's see whether you have understood this with these two questions. Phi of 49. All right. So as per our rule, it is like we can divide it into 5, 7 and 5, 7. 7 is a prime number, so we can apply 6, 6. So this is coming as 36. Is it correct or not? The question is. So the point is that if you are looking at over here at 59, that's the third rule applies when m and n are getting prime. Right? But here if you observe both are like m and n are basically same here. And they are the element. One element is 7 and here 49 is equal to 7 square. So ideally, if you are using Euler's theorem, you have to decompose that using 7 square minus 1. Like we have solved in from the other example. And you get the answer as 42. So 36 will be a wrong answer in this case. So be very careful while choosing out the element. Because 49, you have to divide that because anyway, if you observe that m into n was only applicable for the prime numbers itself. But as 49 is not that, so we cannot do it. That's as simple as that. What about Z14 star? What was that star? What indicates Z14 star? Multiplicative group. So it has that elements which has some multiplicative properties and all. So if you try to solve it with the Euler's Phi theorem for like what is the number of elements in Z14 star? Okay, that's what we are discussing. So we can actually have similar scenario that 14 can be divided into this half 7 and 2. And then we actually have a 2 and 7 which are relatively prime to each other. So we can say 1 and 6. Accordingly, we can say that there are 6 members which are less than 14 and they are co-prime to each other. And in that we can observe that what are the numbers which we can find out. You can do it in your own way. You can take the elements 1 to 14 or rather 1 to 14 and you can check that which are prime to the number itself 14. So if you observe 1, 3, 5, 9, 11, 13, they are not divisible with 14. So naturally they are the co-primes with respect to 14. Alright, so that's how you can do it. So it is applicable to any group for that matter, any elements for that matter. The rule is that using this process, we are going to try generalizing the Fermat's equation. So let's see about that. Now please make a note of this. This is where I started actually. So please make a note of these two equations because these two rules are absolutely same as that of Fermat's Little Theorem, except that you can see the first one itself. In the Fermat's theorem, it was only that a to the power p minus 1 was congruent to 1 of mod p. That was there in the first rule. If you go back to previous day's class, we had that. Here the same thing except that p is now replaced by a phi n, where phi n is an Euler function which is defined by all those rules, the 4 rules that we have discussed. Understood what I mean? This phi n in case of Fermat's theorem, it was specifically for p. Because a to the power p minus 1 congruent of 1 mod of p. That's what we discussed in last day's class. Here what we are doing is we are making it more like a generic. That we are using instead of p, we are using a phi n, where this phi n belongs to the rule that we have discussed right now. All the 4 rules that we applied. So that will become like this. So if you are given a scenario, maybe let's given an example over here. For example, A is 11. A is 11 and N is 10. Now you apply over here, so it will be 11, phi 10, mod 10. Okay, just example, I'll give you next week also. So if this is a scenario, this phi 10 will be calculated with respect to the rules that we have already discussed. So phi 10, if you remember, we had found out something as 4, I'm not wrong. If you go back, phi 10, if you observe here, it's 4. Okay, so what we are doing here is that for 11 to the power, it is usually this way, 11 to the power 10, phi 10, congruent of 1, mod of 10. Is it? Or no, A is 11, right? A is 11, this will be 10, yeah. Kind of. This way we are writing it. So in that way, if you observe that same thing we have written over here, so we can, without even calculating, we can say just like in Fermat's theorem, we were concluding for a very high value that we are getting, we can directly substitute that by 1. Simple as that. We don't need to compute. We'll see that with an example after this. Second rule also, please make a note of it. We are not going to invest much time on the second rule. As I said, this will be directly used for RSA algorithm in module number 4. Please keep a note of it. This is more like when we even reduce the parameters like the condition imposed on n and a. You can see the second one. First one, n and a should be prime. Let's see here. N and a are to be prime. To apply this. In the second one, n and a can be any integer. And here, k becomes an integer which should be multiplied. In most of the cases, this k will be 1. So, we'll see that with an example. So, we can represent that in spot over there. In Fermat theorem, if you go back, second rule was something like this only, where we are being out. So, same thing was there in the previous example. Except that is phi and stuff. So, let's take an example. 6 to the power 24. And 6 to the power 24 mod of 35. Now, it has already been explained over here. A is given by 6, 3 is 35. So, we are applying the first rule over here. Both are prime to each other. So, we are applying a to the power 5n component of 1 mod p. Right? Now, if you observe there that 6 to the power 24, we don't need to compute anything. No need to waste our time. If this is applicable, if we just write that we are using Euler's Phi theorem or the first Euler Phi theorem and we are using it to calculate, then whole thing can be replaced by 6 to the power phi 35, mod 35. Now, if you observe this two, if you compare these two, they are the same because phi n, this should also be n, I think. This I think I mistook. This should be n. Or if this is p, then this should be p, whatever. They should be same. Alright, so this is matching to the template given. Hence, we can directly substitute that by 1 and hence we can write it as 1. Without any computation, anything for that matter. On the other hand, if you take the second example, 20 to the power 62 mod 77. Alright, so in this case, what we are doing is, which I think we don't need to discuss much over here. As I said, we'll come back to this later. What we are trying to do is, we are using k equals to 1 and we are trying to decompose that in a way such that we can apply the second rule on top of it. So here actually, in between there is some steps given. I think I should write it down so that it's easier for you to understand. Let me just write it down because it's not mentioned here. So this is given, right? So we are applying the second rule. So second rule wise, we can write 20 to the power 1 into phi of 77 plus 1 mod of 77. This is given by this. So this 20 to the power 62 mod 77, if I apply the second rule, in between this is the steps which are coming. Now, if you observe this phi 77, we have to find separation. And it will come as 60. We have discussed in the first example itself. So, this if you apply and you break up into different factors, just like we did in the previous examples class, we categorize the power. Okay, so maybe I'll just, if you wish to, I can write it down. So 20, 1, 5, 77 plus 1. Okay. I'm not writing the mod part of it. So this 577, if you compute, it will come as 60. Okay, why? Because 577 is 11 multiplied by 7. So this will be 60. This already we did with the basic formula. So this is 60. So if this is 60 we have, so we can divide it into something like mod of, it's mentioned actually here, 20 mod of 17, 20, this one is a separate, and all together there is mod 77. We are just arranging it, rearranging it a little bit, nothing more than that. And then 577, if you replace that by 60, so 20 to the power 60 plus 1 mod of 77. So the in between step should be 20 to the power 60 mod 77 plus multiplied by 20 mod 77. So there will be two terms of 20 mod 77, one term of 20 to the power 60 mod of 77. And now for 20 mod 60 of 77, you don't need to compute anything. You apply the first rule and you get an answer of 1. That's why it's mentioned as 1. This in between there is 1. So this, okay, I think if people are getting confused a bit, what my meaning is, Acha, let me do one thing. Let me do one thing. I'll do it. 20 to the power 62 mod of 77. That's what we are trying to find out. Is it visible? Yeah. So the point is, first we should write it as 1 into phi of 77 plus 1 as per the second rule mod of 77. Now this can be written as 20 plus 2 means? No, that's what. Here there should be a 20 mod of 77 as well. We will arrange it in this way, right? I'll write it this way only. Does that make sense? 20 mod 77 here. This is 1. This whole thing is 1 mod 77. Now this will be coming as 60. Now if you take the total power, it is 62. So 1, this will be 1 and over here is 60. So 60 plus 1 plus 1, 62 will be the total power. That's what is going on in that in between steps, as I said. Now this 20 to the power 577 has a value of 60. So when you come to 20 to the power 60 mod of 77, this will be 1. So the overall value will be something like, it will look something like 20 mod of 77 multiplied by 1 multiplied by 20 mod of 77, something like this, mod of 77. So now you take 20 and the answer will be something like that. Final answer, whatever you're getting, 15, I think. This is not mentioned over here in any of the steps. Why? One of the reasons what I found is the same thing. Final answer is also clear. The one is also missing and differential interesting this one. The previous, this 577 in this particular example, what we are trying to do is to find out the function and how it can be applied. But as I said, the second rule we are not going to invest much right now. We are not going to invest much on this second rule. This is just I thought of giving you an example where it can be applied. Okay, but later on we will discuss this much in detail. For the time being, you can apply the first rule itself. You can think of the first rule and you can think of it that how we can apply on top of it. Okay. Now the last part that we are left with is the inverse. Yes.
The 6424. 5 of 30 equivalent 23.
5 and?
5 of 35 is equivalent 20.
5 of 35, yeah. Because we are replacing this. No, you can see. You go back. A to the power 5n should be written as like 1 mod of n, right? So in this case, this 6 to the power 24 that you are writing, the same thing. Yeah, we are replacing this 5 25 35. That's one. If you try to find it out, you will get the same answer of that. All right. So now the last one, as again the same thing what we did in the previous example, multiplicative inverse of getting using the Euler's theorem in this case. Please make a note of the last equation. 8 inverse mod of n is given by a of phi n minus 1. Same thing, it was p minus 2 in the previous example. We have taken that. And you can see the same example has been taken. 8 inverse of 77 mod 77. But here we are applying Euler's theorem, not Fermat's theorem. Alright. So the same thing you can see here, 8 to the power 11, 8 to the power in 8 inverse mod of 77. We have to find out the inverse. And here, this is the first step we are doing. And in the same manner, just like I told you, the inverse should be nullified. So that should be generalized to something of a value. So that is replaced by 577. Why? Because your n over here is 77. So phi of 7, okay, phi of 77 minus 1, which means, so this you have to compute. Now the point is, we have already computed 77, right? At least for this example, 577, 60 was the answer. So that 60 has been used over here. So 60 minus 1 is 59. That's why this is 59. Am I understandable here? Phi of 77 we have just calculated as 60. So that 60 has been used over here. So 60 minus 1 is 59. So 8 to 59 is where we stand. Post this, the solution is same as that of common. What we can do for this 8 to the power 59 not 70? Go back to the rule that I told you. You have to decompose in such a manner that any one of the powers should be at least low. Like for example, you can say any one of the solution I'm saying 8 to the power 4 multiplied by 8 to the power 55. 55 can be written as 8 to the power 11 into 5 or 8 to the power 5 into 11. What I mean is, I am writing here 8 to the power 59. So this can be decomposed maybe in one of the steps can be 8 to the power 4 to the power 8 to the power 55. Instead of that, I'm like this, or maybe 8 to the power 4 into 8 to the power 5 to the power 11. Now you compute 8 to the power 5, mod of 77 is there. Same rule. Can you please verify that whether you are getting the answer for this? Because this second part is same as that of Fermat's rule. You can take the value over here and you make sure that it comes to a smaller degrees. Otherwise, this can't be computed. So the same rule is applicable over here. Nothing is new for the calculation part, except that you are applying this formula. If you are using Euler's theorem, if it is mentioned that you have to find the multiplicative inverse using Euler's theorem, then replace this 8 inverse with the Phi-Function using the formula phi minus 1. Right? Where n is the number over here, the base. So pi n minus 1, which in our case was 60, because we computed this 577 as 60 earlier. So 60 minus 1 is 59, so 8 to the power 59 mod 7. Now what I am saying is this 59 needs to be distributed, decomposed. So this 59 can be written as like 8 to the power 4 multiplied by 85. Now 8 to the power 55 can be written as 8 to the power 5 whole to the power 11. Now in this class only we tried solving questions like this. 8 to the power 4, take the value, divide that by 77, get the remainder, okay, keep it in the bracket. So that will be the first element that will come up. Understood? That's what I'm asking you to do. So please compute and tell me that whether it's 29 you are getting. Please check it. Your answer should be 29 here. Whether you are getting the correct answer or not. What will be the value of 8 to the power 5 to the power 11 suppose? Can anyone give me the answer? 8 to the power 4, leave it for the time being. Let us keep it that way. This 8 to the power 5, can you please compute and tell me what is the answer you are getting? I am not sure whether you are doing it properly or not. Take out your calculator, take 8 to the power 5. Whatever the value you are getting, divide that by module 7. Like in our case, it's 77. So you can divide that by 77. Post decimal, whatever the values you are getting, keep that. Multiply that by 77 again. Whatever the whole number you are getting, replace this 8 to the power 5 by that whole number. 40? 43. So it should be 43 to the power 11 like that. For people who are not there on previous day's class, it's a little, not a difficult, I would say it's a different method to be honest. But I don't have time to repeat once again. So basically what we are trying to do, we are trying to make sure the factor which is to the power be reduced in such a manner that it is computed. So here now we have 43 to the power 11. Alright, that also we can reduce. Can I reduce this 43 to the power 11? Anything that you suggest? Maybe 43. Maybe we can do one thing. 84, 43 multiplied by 43 to the power 10. Remember, previous day we took an example, 148 or something was there, 168 or something was there. So now next step will be 43. So we get one number. This 43 to the power 10, maybe like this. 43 square to the power 5. Please do this. So that again, you take the same process. You go on repeating. Then you multiply 8 to the power 4, 43. Remember this 8 to the power 4 is also with mod 77. So please do it. What is the value of you are getting 8 to the power 4 mod 77? Can anyone please give me the value? 15, 1 5, right? Yeah, correct. So this is my 15 value. This is 15. So we get 15, 1. 43 is next. 43 square. Anything you are getting? 43 square? 43 square? 1. So 1 to the power 5. 1. So basically you have this as the whole number. So 15 multiplied by 43, whatever the value, divide that by 77 again. Get the remainder. That will be your answer and that should match to 29. Am I okay with this? The calculation part that we were discussing right now, this has already been discussed in previous day's class for the Fermat theorem. So there is nothing new to it. The factorization, the decomposition of the power to a smaller value is same. Only remember, if in the question is mentioned as use the Fermat Little Theorem, then you have to use the a to the power p minus 1 formula. If it is not, then you have to use the Euler's theorem. But in here it was easy. Why? Because we have already computed 577 in the previous exam. But for example, here you are with phi of 187. So you have to use the rule in order to find phi of 187. What is the value? Understand? That is where the trick comes in. So phi of 127, this value, like here it's coming as 159. Separately we did questions, right? Phi of 187. So you compute accordingly, find the factors, apply rule number 2, 3, 4, wherever it's applied, and then you find the answer. Please practice this kind of questions. Take any example. As I said, there is ever, like, it can go on with these examples. Please try solving any one of them. For example, 71 inverse mod of 100. Okay, please try to solve this and check that whether you are getting the 31 as the correct answer to it or not. Okay, for here phi of 100, because 500 we have found out. 40 was the answer, right? 500 we have done in some time back. So this was 40. That's why you can see the power is 39. Can anyone quickly give me how will you divide this 39? In what factors you will give? 30? Fine. That's also. As I said again, I just for people who are not there on last day's class, there is no, like for here, we have divided it into 8 to the power 4 into 8 to the power 55. That is one of the solution. It's not the only solution. Okay. Make sure that you factorize in your own way. Only that in some of the factorization, if you have considered any value, you might take more number of steps to compute and someone will take less number of steps to compute. Over here, like 4 square to the power 5, we fortunately get a 1. So we have reduced some steps over there. So same way you can choose any factors for that matter, but make sure that you come with the correct answer because the final answer will be the same. So that won't be the change. So there is no such specific rule that how you are going to factorize, that's up to you to decide. Right? This is one of the sample of them. So this is about the syllabus for your CAT 2. Up to this point, Euler's function, Euler Phi-Function, Euler Theorem, Euler Phi-Function, and Fermat Little Theorem. Along with the previous thing, polynomial arithmetic, GCD, Euclidean algorithm, rings, groups, and all those discussion. And the first module where we discuss the existing symmetric algorithms for cryptographic algorithm, Playfair cipher, Hill cipher, Vignay cipher, Caesar cipher, transpositions, substitutions, all those affine ciphers. So all those things are there in your syllabus. Okay? As I said, the distribution is 30 and 20. 30 marks will be from the first module. 20 marks will be all together with all these numericals. Okay? Don't overthink. Just whatever we have discussed in class, similar kind of questions are to be given in your CAT 1 as well. Okay? So don't worry. Very scoring paper. Make sure you get everyone I would expect to get more than 40 in this paper. Okay, so attempt in that way. Okay, fine. So thank you then. So post CAT